Hello, my name is Scott Howard, and I am faculty in the Department of Electrical Engineering at the University of Notre Dame. And in today's tech demo, we'll be discussing a distributed, low-cost, multi-sensor detection, imaging, and analysis network. This network includes both the hardware nodes that will contain the networking and sensing hardware, software to interface, control, and collect data from the nodes, new technology for low size, weight, power, and cost thermal imaging, and all of this compatible with unmanned aerial drones for a distributed, low cost, and a powerful sensing network. So the goal here is to develop a real-time situational awareness from this network. And so the platform features that we have is to consider multidimensional threats through multiple sensor types. The idea here is to have multiple nodes that have many different types of sensors on them. And so that this interface and the networking and the protocols we develop ought to be very generic so that new types of sensors can be added and capabilities can be tweaked as needed for each environment and for each application. And once we have these multiple types of networks and multiple types of hardware together, we need a way to connect these all together through some type of network. And also we want a way to have an ad hoc and flexible on-demand way of analyzing this data, kind of piping it through different mechanisms, as well as collecting this data. And this flexibility is one of the key components of the technology we've developed. Also here is important is this distributed sensing. So distributed sensing is important so that we have no one point of failure. By avoiding centralization, we're also resilient to jamming or interference effects. We have the ability to also combine information from multiple angles or multiple locations to get a better fidelity or signal to noise ratio of the data we're collecting in the first place. But by using distributed sensing, we need network communications to be kind of an important part of the platform. And so this has been built around this need. And so we both want to not be dependent upon any one networking platform, but as also leverage existing ones. So this can use available Wi-Fi networks, cellular networks. It can develop its own mesh networks or its own type of protocols to connect it with each other, as well as store and hold. The sensors nodes can collect the data until it can be either recovered or within range of another friendly network node. And this is important because we really want to make sure that the information gets back to the decision maker in an efficient and complete way. And so having this responsive sensor network allows the controllers to be able to have their the command control and the communications of the network as well as of the environment. So the need we had when we started off this project was to come up with some type of distributed platform for generic sensors. And so any type of sensor we can plug into this, we can use and be able to control the sensors as well as collect the data. But also we have some unique capabilities. We were looking at RF situational awareness. And so we'll talk a little bit about that in the next couple slides. And this is radio frequency situational awareness to identify activity in an area, as well as we developed through alert, low size, weight, power, and cost imaging systems in the mid-infrared, which are useful for chemical detection as well as thermal imaging. So the solution that we chose is to combine the Army Research Lab Notre Dame wireless collaboration called Radiohound, which is this distributed RF sensing network, which already exists, with the technology Alert developed around mid-infrared spectroscopic imaging. And so the first platform we'll talk about is what is this Radiohound network? Well, Radiohound is this collaboration between the Army Research Lab's Electronic Warfare group and their Sensors Directorate with the Notre Dame Wireless Institute. It was funded by the Office of Naval Research, or is currently funded by the Office of Naval Research. And the goal of it was to develop a real-time RF situational awareness, where RF is radio frequency. The concept here is that, that there is a RF environment, radio frequency environment around us all times. Our cell phones and vehicles and technology are constantly emitting radio frequencies into the environment. And so if you could be monitoring this continuously, you can identify when a signature of a threat might be occurring. This might be an increase in a certain type of spectrum or an increase in certain intensity or frequency of communications or contacts. So these signatures could then be used to identify, increased risk of threats for maybe possible further investigation. So that technology was being developed through, this collaboration. And along with it was the hardware nodes that we just saw in the previous slide, and the interface to all the hardware nodes. And here's some screenshots of this interface. And so through a web interface, you can access individual sensor nodes, configure them as needed for whatever sensors are on board for that specific nodes, and as well as collect data from those nodes. And this is an example of a specific portion of the RF spectrum being collected from a single node. These nodes can then be deployed across an area. And so here is a map as part of the interface where these different green markers indicate the locations of different sensor nodes in the environment. And each of these nodes can be individually addressed to turn on, acquire data from, as well as some tools to bring this data together. And so you can look at activity within a certain region of the RF spectrum, within a region, generate some heat maps, as well as if you were to have a threat score, for example, based on the different powers and frequencies that are available, you can actually have kind of a real-time threat score map. And these are things that were developed through this collaboration already and has already been field tested through some campaigns and is a pretty proven platform for distributed sensing. And these already contain the computing power, the networking requirements, GPS, can have fallback networks, as well as the standard network communication protocols. So what we wanted to add to this, as well as leverage this type of platform for a generic sensor interface, was some of the technology developed through Alert, specifically in the area of mid-infrared imaging. So Alert developed these technology where low cost, under $250, under $200, thermal imaging systems based on vanadium oxide microbolometer arrays could be used for chemical signature detection, but also just for general thermal imaging. And so these become very low weight, low power, low cost sensors that are perfectly suitable to be implanted with these Radiohound distributed network. In addition to this, we have also developed technology through Alert to improve the performance of low swap C. When you reduce size, weight, power, and cost, you increase noise, maybe decrease sensitivity. And so we've developed different algorithms to do this. We've developed algorithms both for detection and estimation of different compounds that are present, as well as ways of improving imaging performance in general. For example, we developed a denoising neural network, which will be demonstrated here on this slide. And on the left here is the original data is coming from a sensor node located on Notre Dame's campus, and the right will be through this denoising neural network that was developed. And what this network does is, as data is acquired through the original system, it, as fast as data comes in, applies this denoising system model onto it. And this model was trained with 12,000 images that we acquired of biomedical images, and we're able to use this to apply to this denoising. And effectively what this means is that we can then use these low swap C sensors in sensitive environments with basically an 8-time increase in speed or the signal to noise ratio for more sensitive measurements. We also have the ability to make an adjustable analysis of this data. And so this entire system is built around a broker-subscriber distributed architecture so that each of the sensor nodes can send data out to either detection algorithms, to denoising algorithms, to a control client. And this can be configured by the control client in an ad hoc way. For example, we can set up a system where the raw data can go to the a denoising algorithm, and then this denoising algorithm goes straight to the control client or go to further down the pipe stream analysis. And this is a way that we can adjust this on the fly. And we have implemented this. And so here is a demonstration where we have our control operator in a laboratory on one point of campus. And then we have a sensor node located on campus at a student location. And what we are seeing is that the user can click a button, the checkbox there, and when it does that, the data goes straight to the controller as well as to the cloud. There's a distributed computing cluster somewhere else in South Bend that is taking this data, processing it in real time, and then sending it over to the controller. And so we have this kind of distributed system for acquiring and seeing these images And it's helpful because it's also generic, not just imaging systems, but also any type of chemical sensor would also be useful in the system. And other type of combined analysis would be helpful. You can overlay visible, infrared, in order to make this, whatever information would be required for the user. So in conclusion, we have this now multi-sensor distributed network. The key points here that it leverages low swap C technologies such that it's portable, cheap, and adaptable. Agility is extremely important for this network. It can adapt with different sensors for different environments and different algorithms and different procedures based on the requirements of your situation. It's distributed network, so we can collect the data in a distributed fashion that's resilient to failure and be able to still coordinate with a decision maker at a control point. It's a modular architecture, so we can add sensors and algorithms as needed, as well as the computation itself is distributed. You can then choose to optimize your bandwidth between having high bandwidth data communication and centralized computing, or you can have as much computing as possible done on individual nodes. For example, on the right here is a drone that's compatible with all the technology. This board right here is actually the same board that would control, that we were demonstrating on those individual nodes. And so if we had a limited bandwidth, we can actually do as much computing as we want to on the board and just send the process data. And there's a tremendous number of applications. This started off looking at chemical sensing and spectroscopic imaging, but really, you can think about many situations where you'd want to be able to have a somewhat autonomous or somewhat distributed sensing system. For example, remote monitoring of infrastructure, such as pipelines or energy infrastructures, electric substations. Would be an effective use of this, as well as distributed soft target monitoring, where there might be multiple locations within a region, for example, multiple places of worship, where rather than having significant manpower to monitor each location individually, you can then have this type of command and control, where each sensor node and environment has the type of sensors that are most optimized for it, as well as the sensing algorithms and approaches that are necessary for it. So thank you for your time, and I welcome any questions.